Hi everyone. So let me see in this class the properties of groups. Properties of group. So here there are some properties. In that first one is a theorem. So that is uniqueness of identity. It means the identity element in a group is unique. So in exam they can ask prove that the identity element in a group is unique. Prove that the identity element in a group is unique. Okay. So here I am taking, let Z star be a group having two identities E and E dash. E and E dash. So here I am taking two identity elements, those are E and E dash. So then E is the identity element of Z, of a group Z, then E into E dash is equal to E dash, because E is the identity element. Here E is the identity element, so because of that it will become E into E dash is equal to E dash. Next, if I take E dash is the identity element of a group Z, that implies that E into E dash is equal to E. So here E dash becomes what? Identity element. So from equation 1 and 2, so these two are equal to each other. So therefore E into E dash is a unique element of Z, unique element of Z. Hence from equation 1 and 2 we can get E dash is equal to E. E dash is equal to E, because E into E dash equal to E into E dash. So therefore these two are equal to each other. Therefore E dash equals E. Therefore the identity element of a group Z is unique. Group Z is unique. So 2 mark question will be asked on these type of results. Okay. So next, uniqueness of inverse. So here the uniqueness means the inverse of an element in a group Z is unique. So in exam they can ask prove that inverse of an element in a group Z is unique. Okay. So for this proof, here we have to prove. So means here I am taking, let A be any element of a group G star which has two inverses. So here A be any element of a group G star which has two elements, those are B and C in a group. Okay. So here A inverse is equal to B, that implies that BA is equal to E. BA is equal to E, because it becomes this side, then it will become BA is equal to E. So that is equal to what? BA can be written as AB using commutative law under multiplication. So this will be this one will be A inverse is equal to C. A inverse is equal to C. That implies that this can be written as A inverse is equal to C can be written as CA. So using commutative law, this can be written as, under multiplication, this can be written as A into C, that is equal to what? E. So now I am taking BA is equal to E. BA is equal to E, because here A inverse is equal to B and A inverse is equal to C. So we have to prove here inverse of an element in a group is unique. So therefore here we have to prove B is equal to C. B is equal to C. Okay. So here I am taking BA is equal to E. That implies that, so here C is multiplied on right side. Okay. So multiplying C on the right side, so then we get BA into C is equal to E into C. Okay. Using associative law, we can write this as B into AC is equal to C. So your AC is what? E. AC is what? E. So B into E is equal to what? C, by equation 2. So therefore B is equal to C, because B into E is equal to what? B. So therefore inverse of an element in a group is unique. In a group is unique. So you remember this result, because several times this question have asked in your previous year examinations. So you remember this. So next remark, inverse of the identity of a group is itself. The inverse of the identity of a group is itself. So next, for the additive operation, minus of minus a is equal to what? A. Minus of minus is equal to a. So next result, so that is if Z is a group, then a comma b belongs to Z, then a inverse is equal to a. A inverse is equal to a. And second is AB inverse is equal to B inverse A inverse. Or in several times in examinations, this question I have asked like this: A star B inverse is equal to B inverse star A inverse. B inverse star A inverse. Or this can be asked like this: the inverse of the product of two elements is the product of their inverses in the reverse order. This question can be asked like this also: the inverse of the product of two elements is the product of their inverse in the reverse order. Okay, so let me solve first, that is A inverse is equal to A. So solution for this is, since A inverse is the inverse of A, therefore A into A inverse is equal to what? E. And A inverse into A is equal to what? A. Okay, so that implies that A inverse into A is equal to E. Okay, so that is equal to A into A inverse using commutative law. Okay, so that implies that inverse of A inverse is equal to A. Inverse of A inverse, because so previously we have taken, so here B inverse A inverse is the inverse of what? AB inverse. So here, so A inverse is the inverse of what? A, because this can be written as A inverse is equal to A. A inverse is equal to A, because A inverse is the inverse of what? A. So that implies the inverse of A inverse is what? A. That implies that A inverse is equal to A. So next is second example, that is AB inverse is equal to B inverse A inverse. If star is asked, then we have to write middle of this star. Okay, middle of this A star B inverse star A inverse, like that we have to. If they ask star, so between these two we have to write star here. Okay, since A comma B comma A inverse comma B inverse comma AB comma B inverse A inverse are all are elements of Z. All are elements of Z. Therefore AB into B inverse A inverse is equal to A into, so using associative law we can write this as A into B inverse into A inverse. Okay, B into, so because of associative law under multiplication law. So B into B inverse is equal to what? E, because of inverse law. So A into E is equal to what? Because of identity law, A into E is what? A. So that is identity law. Identity law. So A into A inverse is equal to what? E, because of inverse law. Because of inverse law. Therefore AB into B inverse A inverse is equal to E. B inverse A inverse is equal to E. I take this as equation number 1. So again, B inverse A inverse into AB is equal to, so using associative law we can write this as associative law, we can write this as B inverse A inverse into AB as B inverse into A inverse A into B. So A into A inverse is equal to what? E, because of inverse law. Inverse law. So B inverse into E is equal to what? E, because of identity law. identity law. So B inverse into B is equal to what? E, because of inverse law. Inverse law. So here, so B inverse A inverse into AB is equal to B inverse into A inverse A into B because of associative law. A inverse into A is equal to E because of inverse law. B inverse into E is equal to B inverse, that is identity law. B inverse into B is equal to E because of inverse law. Therefore, B inverse A inverse into AB is equal to what? E. So then these two are equal to each other. From equation 1 and 2, we can say AB into B inverse A inverse is equal to E, and B inverse A inverse into AB. Okay. So because of this, we can write A inverse into A is equal to E. Okay. So here A inverse is the inverse of what? A. A inverse is the inverse of A. So here your AB becomes inverse of what? Inverse of what? B inverse A inverse. So B inverse A inverse is what? AB. So therefore AB inverse is equal to B inverse A inverse. So you remember this. So if star is asked between these two, so you have to write here A star B inverse star A inverse. So that can be written as A star B inverse star A inverse. Later you have to write here A star E star A inverse. So this can be written as A star A inverse. This is E. So here A star B inverse star A inverse. So in the similar manner you write it and rewrite this result again. Okay. So this is the proof of your given theorem. Okay. So next. So this is the generalization of our above result, that is AB inverse is equal to B inverse A inverse. So generalization of that is, by principle of induction, mathematical induction, the above theorem can be generalized as A, B, C, so on P inverse is equal to first P inverse, so on C inverse, B inverse, A inverse. So this is the generalization of your above result, that is AB inverse is equal to B inverse A inverse. Okay. So remark of this is, if the composition is addition, then this can be written as minus of A plus B is equal to minus of B plus of minus A. So here multiplication is there, but if we take plus, then we write minus of A plus B can be written as minus of B plus minus of A. If G is a commutative group, then A comma B belongs to G, then AB inverse is equal to A inverse B inverse. A inverse B inverse, because AB inverse is equal to B inverse A inverse and BA inverse is equal to A inverse B inverse. So here these two are equal using commutative law. So then these two becomes equal. Therefore AB inverse is equal to A inverse B inverse. AB inverse is equal to A inverse B inverse. Okay. So next again a result is there. So that is, if A comma B are elements of a group Z, then AX is equal to B and YA is equal to B have unique solutions in Z. So here I take let A belongs to Z, that implies that A inverse also belongs to G. Therefore A belongs to Z, comma B belongs to Z, then A inverse B belongs to Z, because here A inverse also belongs to Z. Okay. So now we take A into A inverse B is equal to A into A inverse B is equal to, using associative law I can write this as A into A inverse is equal to A into A inverse into B. So A into A inverse is what? A into A inverse is equal to what? E. Because of not identity law, this is inverse law. Inverse law, we can write A into A inverse as E. So using identity law, we can write E into B as B. Identity law. Okay. So therefore X is equal to Therefore, x is equal to A inverse B is a solution of the equation Ax is equal to B, because we can write A inverse B is equal to x. A inverse, because Ax is equal to B, so then we can write, so x is equal to A inverse B. A inverse B. So therefore, x is equal to A inverse B is a solution of the equation x is equal to B in Z. So here we take uniqueness. So let the equations Ax is equal to B have two solutions, x is equal to x1 and x is equal to x2 in G. Then Ax1 is equal to B and Ax2 is equal to B. Then we have to prove x1 is equal to x2. So therefore, Ax1 is equal to Ax2. Okay, using cancellation law, left cancellation law, we can write x1 is equal to x2. Therefore, the solution of Ax is equal to B is unique in G. Unique in G. So in a similar manner, we can take yi is equal to B have a unique solution in Z. So similarly, it can also be proved that the solution of the equation yi is equal to B is unique in G. yi is equal to B is unique in G. So with this, I conclude today's class. If you have any doubts regarding this, you can send questions to my WhatsApp number and clarify your doubts. Thank you.